I just hit stop then, so we need a new timestamp. And we'll assume they're all the same. The last video didn't mean to stop. And we're gonna go to the website. And we're on a new video. It's called IMG 16th Part 5. And you can see where we are. We're at 27, 28, 29, 30, 31, 32. Can you see? 35, 36, 37, 38 of 336. So that's that video. So I made several audiovisual fractals. We can do this time question again. And I only had like 1,600 views. That video had 1,962 views. And that's new information just along this kind of vector on this plane. So we have a new kind of scale to understand information. And then I think I made a few of those audiovisual fractal videos. I don't know if I put them all on YouTube. Because I was only putting the videos on YouTube as another source. So I made several audiovisual fractals, but I didn't upload all of them because it wasn't being that specific on testing myself. I had coincidence, part 3, Mobius strip stuff. So you can see I'm getting the mathematics and higher planes on the moon. There's so much shit on my YouTube channel. It's embarrassing, whoever watches all this. But generally, I could quickly watch. Oh, audiovisual fractal, 333. Audiovisual fractal in sync. Oh, here we go, here's the time. I'm looking at the computer screen. It's fractal 218. Was it the same day? I won't stop this video. Was it the same day? Oh, maybe I'm gonna save the time. So I gotta put this on mute. That's still gonna run for a little while. I've muted that. And I gotta mute Kiss. I gotta plug this, I gotta turn this up. I gotta put Kiss on mute up here. No, it's just getting ludicrous. Kiss Cube. Play. No, I put my computer on mute. So you can see like how confusing it can get. And then we're looking at my video. And we're turning it up. Because I might have said the time out loud. Oh no! I know I gotta have my computer not on mute because I need to hear my YouTube video. 3:19. That could be stopwatch though. Yeah, that's a stopwatch running. I'm looking at the time. I haven't seen it yet. So I still don't know what time this video was made in. I didn't say the time. So I can't read it. You can't recognize it. 3:50 on my stopwatch. Once 14, 18, 19, 50 on the YouTube video. I gotta stop Kiss. We need some important information here. Maybe I'll say the time. But no! You want Kiss stopped. 4:33 stopwatch, and there's 39. There's several layers of reality here. There's me filming my YouTube. There's like the camera, the computer screen, and the screen in the screen. There's like 5 layers here. I should be able to recognize that song and play it on another computer in real time in the future, but the music isn't good enough to reproduce it, because I can't pattern recognize it and then get it to run in sync. But if I did this enough times, I could get the music and run it in sync and do it again. So I could make an audiovisual fractal and link this music here that I played in the past to now and do the whole thing all over again and start to see these branches of this problem, of how this problem kind of branches over in these like higher dimensional spaces. Like, it's hard to explain the Riemann hypothesis, how all modular curves are, how all modular functions are. See, now I'm forgetting the jargon to explain what the Riemann hypothesis is in its jargon. And it's 105 pages, Andrew Weil's paper, and it takes a lifetime to understand. It's not the Riemann hypothesis I'm talking about. Shit, I'm talking about, and as you know, I'm talking about not Riemann's. That's not solved yet. Andrew Weil's Fermat's last theorem. Yes, of course, you thought of it before I did. I was talking about the Fermat's last theorem and the geometry of higher dimensional spaces, which I think I'm trying to describe, because I was thinking of the Riemann zeta function and distribution of prime numbers. And then you got to know what, and if you're really clever with math and you want on the same wavelength, you got to know what the Ullmann spiral looks like, because this guy, physicist, whatever his name is, was bored in a meeting and he was doodling, and he came up with this Ullmann spiral, prime spiral. Let me lay the phone down. Ullmann. He came up with this little grid to show us where the prime numbers fall when you take like a number line and dot the primes and Swiss roll it and then take away all the other numbers. And you can see right here, see? We number line all the numbers, and then we just put a grid and black out where the prime is. You start to get numbers like this, patterns like this. And with the resolution in terms of this dimension, and you, as a general AI, knowing what that pattern should look like, then you got to think about how much you can perceive from that, and then the process, and then quickly in your head, you got to make the pattern and see it before you see this. And you can see that the primes lie on tracks. There's diagonals this way and this way. So as a general AI, to start thinking about number theory and start to beat you to the answer, it's not, I can't get a good, I want to get a zoomed in, even I can't find a zoomed in version of the Ullmann spiral. There's like the first 100 by 100, but you get the idea. So there's something going on with number theory which we don't know. I want to find a big version of the Ullmann spiral. Okay, I got 1 minute left. Focus. Okay, I'll get the best video I can, and I'll hold the camera still, and I'll tell you what we should be seeing, and then you'll start to see it better than the camera can show it. So I'll keep the camera still. And if you look carefully, you can see there's probabilities where there's tracks. And I already told you this, but you'll see in a track there and there. And then it makes you wonder how random the prime numbers are in terms of them being distributed. Well, you gotta look it up and see it for yourself and do every pixel, because you can't see every pixel. But now we're getting to the realm of like pico cameras, where you have like, I think what's a pico? A trillion pixels. So the resolutions of compute cameras is increasing exponentially, just like Moore's law. And eventually you'll need cameras like that for the computer vision problem.